TC. And as a result, Anderson criteria gets slightly modified in the sense that because the lattice constant changes with particle size, this would have been the standard Anderson criteria given by the solid line, and this would be the critical length below which superconductivity shouldn't exist. But now we find that because there is expansion of lattice, if it's a weak dependence on the of lattice constant on the size of the nanoparticle, you will just prolong the crossing at which the Anderson criterion occurs. But if you have even further stronger dependence of the lattice constant on particle size, you will basically have superconductivity even at lower sizes. Okay, so that's the sort of explanation that we have for the existence of superconductivity well below the Anderson limit on the size.
It's because we are renormalizing the gap.
That's right. Yeah, that's correct. So that's what is happening. The Kubo gap gets renormalized noticeably due to as well. Yeah, both gaps renormalized, and they go in the opposite side, right? Because the lattice constant increases, it goes other way, and that goes the other way. Yeah. Okay, so the last topic I'll very quickly cover is mechanical behavior, and that's probably the most common experiment that you may come across in day-to-day life. And in particular, I'll be telling you about HCP metals, which are very interesting in terms of their mechanical properties. So when I say mechanical behavior, I'm not talking about linear elastic properties. Okay? These are non-linear mechanical properties, which basically are known as brittleness or ductility of the material. And one simple way to think about this complex phenomena, by the way, ductility is a fairly complicated phenomenon which involves processes that occur at many length scales. So one simple way we look at it is if you start with a bulk material like this and you apply a force on one side of it like this, it has two possible processes with which it can fail. One is, I'm sorry, it can just cleave and create surfaces like this, and in one it will slide, the first half of the material will slide with respect to the other half. So in this case, basically it's the surface energy that is relevant, and that gives you brittle fracture, or rather what is called as crack propagation. And in this case, you basically get a slip mechanism which gives energy surface which has a periodicity of the lattice as shown here. And the energy barriers that you get along these slips basically control what is called as unstable stacking fault energy, which control the nucleation of dislocation in a material. So ductility is caused by dislocations to nucleate and also move, and brittleness is caused by basically the crack propagation. Okay, and crack propagation is described by cleavage energy or surface energy. So this behavior of a material typically involves competition between crack propagation and dislocation mechanism. So why are we looking at HCP metals? Because they are typically lightweight metals. HCP metals typically occur in the left-hand side of the periodic table, which are all lighter set of elements than the others. FCC are on the right. And unfortunately, they have a big ductility problem. Although they are lightweight and very attractive for aerospace applications, their ductility is a big limitation, and the origin of it is the fact that HCP structure is a structure which has two atoms in its primitive unit cell, okay, as opposed to FCC or BCC, which have only one atom in the unit cell. And the symmetry does not permit it to have enough dislocation systems which will give you plastic flow in a material in an easy way. However, nanostructured HCP metals show enhanced ductility, as was shown in this paper. And the question we asked is why? Again, lack of time, I'll be going quickly through this. So what we did is basically studied these two phenomena in these two units. One is called bulk HCP metals, where we use stacking fault and dislocation systems which are far away from each other. And in nanoscale, what happens is you can have two dislocations which are pretty close to each other, and they can have fairly strong interactions with each other. Okay, and that's about 10 nanometers that we looked at. So you have strain-mediated interactions between neighboring dislocation systems, and that can release large stresses is what we show by occurrence of coherent shearing process. So that's what is our main finding. If you take nanoscale HCP metals and apply the shear force as shown here. You basically stabilize this polytypic form. We predicted 3 polymorphic forms of titanium here, and these are basically arising from stacking faults which are here and interacting with each other very strongly. The color code basically tells you the degree of strain in this lattice. So just like ferroelectric materials had inhomogeneous order in nanoscale, what we find is HCP metals can also have inhomogeneous strain fields in the nanoscale, and that gives rise to totally new structural form of these metals. And
When you say nanoscale,
yeah,
how do I visualize small nanoparticles?
yeah. So, right. So what actually the experiments which show enhanced ductility is basically submicron particles. So they are still very big. So what we changed, Pratap, is the distance between two dislocation systems or slip systems is on the scale of a nanometer. Yeah. Those will be outside what we do now. Yeah. We are looking at a single grain and yeah. Yes, what experiments were done on a nano rod of titanium, and there they could see this very similar thing, although they interpreted it in a different way. So there were no grain boundaries in it. It's a nano rod of titanium, and that's where they.
Micron size, the material is micron size particles.
Yeah, submicron. Yeah.
But the measurement is done on one single or the
Yes, one single rod, which is a continuous chunk. So basically what we find is instead of nucleating dislocations, you can have inhomogeneous strain here and new polymorphic structures which can accommodate fairly large shear strains in these metals. Okay? And the energies of those polymorphic forms are fairly low. It's like less than a milli eV per atom, and we reproduce it with different methods that are available, and it's quite a robust result. And it applies to all the HCP metals except for zinc. Okay? Zinc is a very anomalous HCP metal in the sense its C by A ratio is totally different from the ideal C by A ratio of HCP structure. Okay? Yeah. Then we did lots of analysis to find out. In fact, the difficult part was to prove that it's a different structural form because it's so similar in terms of coordination number and all. So this is what we find for other HCP metals. And you see the C by A ratio of zinc is very off with respect to the others. And this is the only exception to the rule that we found, that polymorphic mechanism. Okay, so I'll close my talk by summarizing that the mechanism that we found for nanoscale ductility of HCP metals involves what we termed as multiscale nonlinear elasticity or hyperelasticity. So typically, you write down a generic free energy function in terms of acoustic phonons like this, and strain is basically given by the wave vector times acoustic phonon, and if you basically expand it, you have to have nonlinear terms, which gives you instabilities in the acoustic phonon branch. You see, we are applying shear strain here, 0.02, 0.04, 0.12, and you develop an instability in the acoustic phonon branch, and that's what gives you the stabilized polymorphic forms, which are inhomogeneously ordered. Okay? So that's what is basically the conclusion of the last part. HCP metals except zinc exhibit polymorphism, which results from straight interaction, and that is what gives them enhanced activity at nanoscale. And this constitutes a new mechanism, which also we mean the experimentalists should reinterpret their HRTEM images in terms of these new structural forms. So to summarize my entire presentation, I hope I have given you some idea about how first principle simulation techniques can be used to obtain insights into evolution of ferroelectricity, superconductivity, and mechanical behavior at nanoscale. And it's quite a powerful approach. It has predictive power as well. And I finally thank my collaborators. Most of the students who worked on it have graduated and moved on to postdocs. Krishna Mohan was a master's student who is now doing PhD in Korea. Sudhanshu and Kushan's group who did the experiments on tantalum conductivity. The new density functional work that I showed was in collaboration with the groups in Temple, John Purdue, Mike Klein, and Saifan Wu. The open source code which we developed for ferroelectrics was with Takeshi Nishimatsu and Yoshiyuki Kawazoe. And the last bit of work on HCP metals was done with a metallurgist, Upadrasta Ramurthy from IISc Bangalore. Thank you for your attention. It's quite similar. Of course, after trimerization, it's very different. See, trimerization gives you molybdenum distance, which is much smaller than what you have in the 1H form. The trimerization means you have bonds between molybdenum atoms. And that's what opens up a gap in the d orbital bands of molybdenum, because the frontier states are all d orbitals of molybdenum. It's the trimerization which opens that distance is smaller in 1T structure. But MOS distance is roughly the same. Okay, 2H is the most stable form. So if you generally make MOS to that's the form it will take. 1T structure, people had made use by what is called as lithium intercalation. This was in 1999. Actually, after we did this work, we found out a paper by Mercury Kanatzidis where they had done lithium intercalation to study MOS2, not with the intention to see whether 1T form stabilizes, but they did see trimerization, which is what is our prediction. Okay, so that was long ago. Now, Arindam Ghosh's group in IISc has stabilized this form by what is called as heterostructure growth. They deposited MOS2 on boron nitride, and that seems to stabilize 1T structure at least in sizable forms, not in the entire sample of MOS2, but notable size. In 1T, that is yet to be observed. Our prediction is yes, it should be ferroelectric. Okay, but some of you may be wondering, how come in perovskite oxides you don't see ferroelectricity as you reduce the size? You get inhomogeneous ordering. And in MOS2, I'm predicting is the thinnest ferroelectric of the world. The reason for it is very interesting and fundamental. In perovskite, ferroelectric ordering is the primary instability in the system. Okay? And that is suppressed by the depolarizing field. In 1T MOS2, it's an improper ferroelectric where the primary instability is trimerization of MOS, which is not polar intrinsically. So that instability is not suppressed by the surface charges that you would have. Okay? And the inversion symmetry is broken as a nonlinear order. So secondary order parameter is ferroelectric polarization. So that's why you can support ferroelectricity in 1T MOS2 even in the thinnest possible form, but not in perovskite oxides. No, not after trimerization. What we show is centrosymmetric 1T form is unstable. And the reason for it is the nested Fermi surface.
So that would be a ferroelectric with the moment in the plane.
Perpendicular. See, that's the spectacular thing. That is normally, yeah.
It will have some corrugation. Physically, will it remain flat?
Very slight corrugation will be there. Yeah, sulfur atoms do show inequivalence Z positions. Yeah.
Any other question?
There are other 2D materials which are multi-lash.
Yes.
Radium,
They are often metallic, Arnav.
radium sulfide, radium selenide, do come in the multi-lash thing, but they are
Right.
probably not ferroelectric.
Very good question.
How much simulation does it have?
No, lots of, including my group, we have done worked on RES2 also. And indeed, that's a very good question. Let me explain what is happening. See, if you look at the phonon dispersion of 1T structure, there are two important instabilities in it. One is at the K point and one is at the M point. So if you have K point instability, which is the strongest as in MOS2, you get ferroelectricity. that K point gives you this trimerization. M point gives you root 3 by 1 type of structure, which doesn't break inversion symmetry. So that's what happens in RES2. So you are absolutely right. RES2 is also a distorted 1T form, not not a pure 1T form that I had. Yes, people have tried to dope MOS2 with RE to stabilize 1T phase. Use rhenium substitution in molybdenum sulfide to stabilize 1T phase. Yes, Push.
Firstly, a comment to Buddha. It is not correct to say that the axis limit has shifted by 40%. We have not seen suburban activity by vanishing down to some particular size within 40% over. It is probably much lower than that because there are a couple of points which show that the TTC has almost flattened out.
Right.
So it could be, we could not measure to much smaller particle sizes, so we don't know. It could be good. So but the questions to you are as few as possible are many questions. One is that there is very interesting thing about the phase transition in perovskite ferroelectrics. If you study the phase transition by Raman spectroscopy, which looks at the distortion, territorial distortion, the ubiquitous Raman reacting on the
Correct.
So it's a very sensitive technique to find out the phase transition. You actually see a slightly higher DC than you see by others. Because there is a sort of dynamic distortion
Yes.
till about 5 or 6 degrees.
That's right.
Do you see that?
Yes.
Calculations are very sort of
Okay.
sensitive here.
No, we have not done phonon calculation as a function of temperature above Tc, Prashant, but the dynamical distortions we have worked